In this video, we are going to talk about the second part in the subtopics 5.4, the fundamental theorem of calculus. In this example 7 and example 8, we are going to calculate the area enclosed by the function between the curve and the x-axis. Let us first look at example 7. There are actually two questions in the example 7. The first question A is to calculate the definite integrations of the function between 0 and 2 pi. This is quite straightforward. The second part of the question is to calculate the area between the graph and the x-axis. These are two different questions, and hopefully by answering or illustrating the solution to A and B, you can have a clear idea of how to calculate the area of a function that in which the functions would have a negative sign. So let us discuss the preliminary of the integration for the area before we zoom into the details of the solution to example 7. So far, we have defined the integrations of the functions in an indefinite integration between A and B. And I have already told you, assume that if the function is continuous between A and B, and if the function f is positive for x sitting between A and B, then the area defined between the function and the x-axis, which is the shaded area, is then simply equals to the definite integrations of the function f over interval of a and b. Here, the area are represented by the symbol a is a positive number because area must be positive, right? So when I talk about area, it is to be understood that the area is the area expressed in the unit of square of the length unit, say 5 cm square, 10 cm square. You cannot have an area which is negative. Say you can't have an area of negative 5 square feet or 5 square meter. So you have to make a distinction between the area of a function defined between the curve of the function and the x-axis. The area and the definite integration of the function is the same only when the function f is positive over the range of integrations. However, for a case such as this one, say you have a function, say like this, okay? For such a function, there are area or they are say between a and b, okay? So in this case, you have a function of fx, and for x that is sitting between a and c, the function is positive, whereas for x sitting in c and b, the function is negative. So in this case, the area under the curve of f between the area of the function defined by the curve between a and b are not simply given by the definite integrations of the function between a and b. This, in this case, will no more be defined as the area for the functions between the curve and a and b. In this case, you have to separate the area into A1 and A2. So here A1 and A2 are separately defined the area of the curve in the region A and C, and the area of the curve between C and B. So here A1 is usual, since A1 is defined for the function that is positive. So between A and C, this is correct. That is, the definite integrations of the function between A and C is just equals to the area. However, for the area of A2, it is to be calculated as the integrations of the function fx between C and B. And it is understood that the function of f of x between C and D is negative. Therefore, this integration will give you a negative number. Therefore, you cannot equate the area to a definite number. So usually what you do is you take the absolute values of the indefinite integration for the function between A and B. By understanding that in this case, the function is uniformly negative between C and D. Then when you finish integrating the function from C and D, then you just take the absolute value. For the case of A1, there's no difference between whether the function integrations is evaluated with a absolute sign or not, because this is always positive. Well, the essential point here is that you have to revert the sign of the definite integration for the function where it is negative, right? So if you are asked to calculate the area of a function over some interval, in this case intervals over a and b, in which the function could have positive sign or could have negative sign, you have to separate it into the sections of the function where it is all positive or where the function is all negative. Then you integrate these functions separately in their separated region. Then you only take the absolute values of the definite integrations of the function within their respective range. So here, let us look at the example 7. So here the question say you have a function y equals to sine x, and we are asked to calculate the definite integration of sine x between 0 and 2 pi. So here you are not asked to calculate the area of the function between 0 and 2 pi. You are simply asked to calculate the definite integrations of the function between 0 and 2 pi. In this case, it is not, this integration is not defining the area of the curve. It's only defining an definite integrations of an function between two limits. So here, according to the fundamental theorem of calculus, if you are given some integrand function fx to be integrated between a and b, the answer to the definite integration is obtained by first knowing the antiderivative to the integrand function. Here the integrand function is f, and the capital function here is the antiderivative of the function. So by calculating or knowing the antiderivative of the small function, then you evaluate the antiderivative at the upper limit, and you calculate the antiderivative at the lower limit. The difference would then be the definite integrations of a small function x. So here you have to first find out what is the antiderivative to the sine function x, the sine function of x. So given small function as f, the antiderivative, which is capital function f, is just equals to minus cos x. Minus cos x is the antiderivative to the small function f, because by taking the derivative of minus cos x, you will obtain sine x. Now, once we have worked out the antiderivative of the sine function f, which is minus cos f, then this definite integration is then equals to the antiderivative evaluated at the upper limit minus the antiderivative evaluated at the lower limit. Here we have capital F at 2 pi, which is minus cos of x at 2 pi. So this is the antiderivative evaluated at 2 pi minus the antiderivative. So let me write off these statements here to make place for me to write down my calculations. So f of 0, capital F of 0, is then equals to the antiderivative evaluated at x equals to 0. So that is this. So cos of 2 pi is minus 1, and then you have minus minus, you have plus, and you have cos of 0, which is 1. So you end up minus 1 to 1, which is 0. So it is understood then the definite integration of the sine function from 0 to pi is just 0. So now we are going to the next questions. We are asked to find what is the area of the sine function over the range of x between 0 and 2 pi. Therefore, you have to separate the calculation into two parts. The total area is understood to be contributed by the area of a1 and a2. A1 is the area of the function, which is sine function, calculated and integrated between 0 and pi. Here is the pi. After x move from pi, from here to here, the sine function will change to negative. Therefore, the area A2 is the integration of sine x dx calculated from pi to 2 pi. This is giving the definite integration for the sine function between pi and 2 pi. However, it is understood that the sign is negative for this region. Therefore, the A2 has to be calculated to be the absolute values of the definite integration, because this is negative for x lying between between pi and 2 pi. Therefore, you sum up A1, which is given by this integration, and A2 is the absolute of this. So you can then calculate this quite easily. So this would be the negative of cos x calculated between pi and 0 plus the integrations of antiderivative evaluated at 2 pi and pi. So this is the integrations of this. Okay, this will give you the value of the integration, but you don't forget about the absolute value outside. Okay, so here you have cos of minus cos of x evaluated between pi and 0. So this could also be equally written as 0 and pi. So that makes things looks much more comfortable to me, where I find it sometimes difficult to have a minus sign in front of the function. So I throw away the minus sign by reverting the order of the lower limit and upper limit. And likewise, this is the same. I have cos of x evaluated between pi and 2 pi. So here I again throw away minus sign by exchanging the positions of the lower limit and the upper limit. And what I have here is cos of 0 minus cos of pi. So that gives me this term, whereas the other term sitting inside the absolute value, sitting inside the absolute bracket, is this. And what is this? This is again cos of pi minus cos of 2 pi. Okay, so then what I get here is I have cos of 0 is 1 minus cos of pi is minus 1. So here I have 1 minus minus 1 plus the absolute sign with cos of pi. Cos of pi is minus 1 minus cos of 2 pi. Cos of 2 pi is actually 1. So here I have 2 plus absolute of 2, which is 2 plus 2, which is 4. Therefore, what I have concluded is that the total area of the function sine x between 0 and 2 pi is given by the area of a1 and a2. And I calculated that indeed a1 is equal to 2 A2 area is also equals to 2. Therefore, when I sum them up, then I obtain area A, which represents the total area of the sine function between 0 and 2 pi. The important thing to note is that to calculate the area of A2, when you perform the integration from pi to 2 pi, you have to revert the sign of the definite integration. So that is how the calculations for example 7 proceeds. Mind you, so here is the solutions to the example 7. This is another example. You have a function of x cubed minus x squared minus 2x. So before we proceed with the calculation, it will always be instructive to look at the functions of f to be integrated over the region of -1 and 1. So this is how the function looks like between -1 and 2. So -1 and 2 is the lower limit and upper limit of the function. And your job is to calculate the total area of the functions bounded by the curve and the x-axis. So in this case, you have to know the region where the function is positive and the region where the function is negative. And here, the function is always positive for x lying between -1 and 0, and the function is negative when x is lying between 0 and 2. Therefore, to calculate the total area of the function between the curve and the x-axis, you have to first find out the zeros of the function, and then you have to investigate the sign of the functions between the zeros. So the zeros will separate the functions into a few parts. So the zeros are the values of x where the function is equals to 0. So you can see quite easily that at x equals to 0, x equals to -1, x equals to 2, the function are all 0. Okay, so then you look at the sign of the function that is separated by these 3 zeros. So there are 3 zeros, therefore you can separate the function into a few regions. And then you have to look at the sign of the function in region 1, region 2, region 3, and region 4. And you have to be clear in which region the function is positive and in which region the function is positive. So you look at this curve and it is quite true that the regions between here and here function is positive, between here and here the function is negative. So when we go back to this, fortunately the function that we are looking here is that we are only asked to integrate between -1 and 2. Therefore, we can ignore this region, we can ignore these regions. Here is -1, here is 2. So by looking at this curve in this drawing here, it is understood that we have to determine only the sign of the functions in region 2 and in region 3. So you look at the functions in region bounded between -1 and 0, the function is positive. Whereas for the x sitting between 0 and 2, the function is negative. Therefore, here the function is positive and the function is negative in this region. Therefore, to calculate the total area of the function, you separate the area into the integrations from 0 to from -1 to 0. This represents the area where the function is positive. For calculating the area bounded by the function between 0 and 2, then what you have to do is that you integrate the functions from here to here, which is from 0 to 2. Integrate it from x equals to 0 to x equals to 2. But you understand that the functions is negative within this region. Therefore, the area contributed by this part of the function has to be placed inside an modulus. So the first thing you have to do to calculate the area of the functions between -1 and 2 is to first find out the region where the function changes sign. And once you have determined the region where the function is positive and the region where the function is negative, then you can write down the definite integration that defines the area in the negative region as well as the area in the positive region. So this is what we have done so far. This is the area that comes from the positive region, and this is the area that comes from the negative region. So then you can straight write down the formula for calculating the area in the positive region. So you just have to integrate the functions. Then the integration of the function could be easily obtained by knowing the knowing the antiderivative of this function. Given a function of x cubed minus x squared minus 2x, then you can actually work out the antiderivative of the function. The antiderivative of this function is x power 4 minus 4 minus x power 3 over 3 minus x squared. So this would be the antiderivative for the integrand function x cubed minus x squared minus 2x. Once you have identified the antiderivative of the integrand function, then you evaluate the antiderivative between 0 and 1 to obtain the values of 5 over 12, which is the definite integration for the function between 0 and 1, and that represents the area of A1, which is this area. I call this A1. And then to calculate the area of A2 here, then what you need to do is simply to evaluate the integration of the function between 0 and 2. Then you take the absolute values of it. That will give you the area of the function in the area of A2. Therefore, you sum up the values of the integrations for A1 plus A2. That will give you the total area. So A1 is given by this number 5 over 2, 5 over 12, whereas A2 is the absolute values of the integration of the function between 0 and 2, which turns out to be 8 over 3, where 8 over 3 is the absolute values of the uh, negative of 8 over 3, where negative 8 over 3 is the result of the definite integration of the function in the negative region. So you add up this one, it will give you the values of the area for the functions x cubed minus x squared minus 2x. That is the example of how to calculate the area of the functions. So to conclude this part, if you are given a function which may contain some positive or negative regions, and if you are asked to calculate the total area of such a function, then you have to first identify the regions where the functions is positive and negative. Then you separate the integrations into the region where the sign changes. So in this example, I will say this is the region 1 and I call this region 2. So here the function is negative in region 2. Therefore, the area of A2 is then equals to the absolute values of the integrations in region 2, whereas for the region 1 where the function is positive, then the area is just equals to the integration without the absolute sign. So that is how we deal with questions of calculating the area enclosed by the function and the x-axis.